Well, good morning or good afternoon to everyone. You know what I'm going to present is to do with Pico balloons, but it's an interesting aspect because we use WSPR to find out where they are. And of course, we want to send a lot more telemetry, and WSPR doesn't cater for that on the face of it. It only has 3 fields. That is the call sign, the grid, and the power level that you're transmitting at. So this whole paper is to do with how is this achieved. Let's just get this down here. So the agenda is I'm going to show you a typical Pico balloon setup, the hardware, and then I'm going to explain the standard telemetry that came out of this. And how to encode it into WSPR packets, monitoring them, and then eventually showing how there's an extended telemetry where you don't have to use the basic, which is fixed for everyone who's using it. And then one slide to do with some science that you can extract from this. So BCAR is the sort of acronym for Balloon Carrying Amateur Radio. And around the world, amateurs build tiny radio payloads and launch them into the stratosphere, which is about 14 kilometers to 50 kilometers, using a Pico balloon filled with helium or hydrogen. And a typical payload is a WSPR beacon transmitting on 10 or 20 meters usually, at only a power of 20 milliwatts. And it's powered by 6 tiny solar panels, each producing about 0.5 volts at 400 milliamps, with a total of 3 volts. However, in full sunlight, you can get about 4 volts. And this is the only means of power usually on a Pico balloon. There's no battery on board, hence the payload only transmits during daylight when the sun is shining. So this is a typical balloon, like nearly 1 meter in diameter. And here you can see I've pumped it up with just plain air to stretch it and get all the wrinkles out as a step 1. And then I store it inside the house for a few days to make sure that it can maintain this pressure and there are no leaks. And the typical payload, as mentioned, is a WSPR beacon. And on these Pico balloons, we use a Raspberry Pi Pico. It's just cheap and easy to program. And there's an add-on board that we get from Triqueta, which contains a GPS, a radio transmitter, and a voltage monitor. The radio transmitter is actually very simple. It's one of these synthesized oscillators, and we simply use two of the 3 oscillator outputs configured to be 180 degrees out of phase, and tie each one to one leg of a half-wave dipole. Hence, we only get 20 milliwatts, which turns out to be perfect. You'll see in the next slide, I think, that you can pick this up all over the world. I've typically been using a 10-meter band because then your dipole only has to be 5 meters. And as you can see from that little diagram there, the balloons on top, you've got half of the dipole as a tether point to your payload, the electronics, and then the other half of the dipole is dangling beneath you. And you've got to keep all of this light. So these dipoles are made out of like 32 gauge copper wire. So very delicate. It's best not to have them too long, but a lot of people run it at 20 meters too. So this is what it looks like. And here is one dangling in my garden, just with a temporary yellow HF antenna. And you can see the copper piece at the bottom, that's the GPS antenna. And there are, of course, the solar panels. So just to show that using pure WSPR, which was developed by Joe Taylor K1JT, is a great way to monitor the balloon, as there are already tens of thousands of amateurs around the world who have automatic WSPR receivers listening 24/7. So there on the right, you see a balloon, the red dots being the source of the WSPR signal, and the white dots are the people receiving it. And that's just 20 milliwatts. But of course, I suppose the height helps a lot. in getting your propagation there. The great thing about WSPR is you don't have to have the sole receiver for your balloon. No matter where it is, someone is picking it up. So it is a neat way to transmit telemetry, but how to do that? So in early Pico balloon tracking, a guy by the name of Andy, he pioneered a long-range Pico balloon tracking system using JT9, the other well-known protocol within WSPR, but it was a heavily modified protocol. And this necessitated anyone who wanted to receive it had to have this specially modified version of WSJTX to be distributed to them. So this is not an ideal situation where you need special software, which of course would limit the number of people receiving these signals around the world. A much better way would be to use WSPR, which amateurs pick up and report to the WSPR database automatically without knowing what the real content is. On the face of it, it just looks like a call sign, a grid as usual, and the power level. So Hans Summers, a G0UPL, he proposed an innovative twist that you encode all this telemetry that you want to send into WSPR-like packets, allowing the global network of existing WSPR monitoring stations to unknowingly receive and upload the data to the WSPRnet database without needing special receivers or software. The way it's done is you would still send a standard WSPR packet, which of course contains your location and the call sign who's sending it, and then followed by a specially repurposed WSPR packet containing the encoded telemetry. And that is sent immediately. And this happens every 10 minutes. So the first 2 minutes would be your standard WSPR packet, followed directly afterwards with a 2-minute telemetry packet, a total of 4 minutes. So just to recap, a WSPR message is a 6-character call sign, which occupies 28 bits to be encoded, a 4-character maidenhead grid locator, which is 15 bits, and the power level that you're transmitting it at, which is 7 bits. And these 3 fields combine to form the 50-bit message. This 50-bit message is convolutionally encoded, interleaved, and combined with a synchronization vector to produce 160 symbols, 62 symbols, which are transmitted using 4S FSK modulation, which is 4-tone frequency shift keying. And the symbol rate is 1.4648 baud, which if you calculate it out, it's a total time of 110.6 seconds, and it uses about 6 hertz of bandwidth. So it's just short of 2 minutes, but these WSPR messages are sent on the boundary of 2 minutes. So Hans's idea was to, as I said, transmit a standard set of telemetry. So this is what he settled on. He would send a locator 56, which means it's the last 2 characters of your 6-character grid square of where the balloon currently is. Because the 4-character one grid square is not very accurate. So those extra 2 characters makes a big difference. The altitude, the temperature, the voltage, and that means the voltage of the solar panels, so that you can get an idea of how good the sunlight is up there. The speed you're traveling at, which is derived from the GPS that you have on board. And then 2 bits, one to say whether, in fact, when you transmitted this particular entry, you had a lock on the GPS. Because it does send even though you don't have a lock. And then finally, he catered for the situation where eventually his telemetry, which is called the standard telemetry or U4B, is not going to be the only one. So this field called header telemetry type is either a 0 or 1. And if it's 1, it means it's his standard telemetry known as U4B. And if you set it to 0, then the packet can actually contain anything you like, which we will getting onto. So now that you have decided on this telemetry, but how do you encode this to WSPR? So as I said, the plan is to make the telemetry packet look just like a WSPR packet. And after identifying these 7 telemetry fields in his U4B telemetry, which of course is much more than the 3 we have in a WSPR packet, which is the call sign, the grid square, and the power level. So how is this possible? Well, Hans's approach was to use the technique called mixed radix packing of telemetry data items to form a large, big number, which is a reversible representation of the telemetry. Right, so now we have a big number which represents all of this telemetry data. But now how do you still get that to 3 WSPR fields? Well, you use mixed radix unpacking into these 3 standard WSPR fields, i.e. the call sign, grid locator, and power level. Real-world measurements, temperature, voltage, pressure, etc., are continuous or high resolution, so they must be mapped to bounded integer ranges, that is, normalized and quantized in order to send them digitally. So selecting suitable step sizes leads to the following quantization of the 7 telemetry fields. So locator 56, which is the last 2 characters of your grid square, can be A to X, so that's 24 squared combinations or 576 values. Altitude, it was decided to standardize on from 0 to 21,000 meters roughly in steps of 20 meters, which gives you 1,068 values. Temperature -50 to 39 degrees centigrade in steps of 1C, which is 90 values. The voltage, 40 values. The speed in steps of 2 knots, which gives you 42 values. And then, of course, you need these 2 flags, whether the GPS is valid and whether the telemetry packet is type 1 or 0, and both of those are 2. So the process is to use this. Step 1 is to use mixed radix encoding of the telemetry data items to produce this big number. And the way that the radix refers to the quantization or the number of values per telemetry value. Then once you've got this big number, you unpack it using mixed radix decoding of the big number that was produced in step 1 to produce these 3 WSPR fields. But the decoding, instead of the quantization you use there, is of the 3 fields in the WSPR packet: call sign, grid, and power level. And it's called mixed radix encoding and decoding because each field is different. So they're not all base 10 like in the usual number system. As I showed earlier, the speed is like 42 values. So you can think of the radix there as 42 because there's 42 values. So how is this done? Well, just simply showing it, it's a little simple mathematical trick. You take this big number that you're going to reach and you multiply the first variable by its quantization or the number of values and add that to the big number. Sorry, let me rephrase that, that's not correct. So you take the big number and if you think of it, if you're in the middle of it, you have to make space for the new variable. So you first multiply it by the quantization or the number of values of the current variable that you want to encode. So if it was V2, you take the current value of the big number, multiply it by its quantization, like 1068 values, and then you add in your variable. And this becomes the new value for big num. So of course, the very first step when you start with V1, the first variable, is not really required because big number starts at 0. So it's simply equal to V1. So you land up with this large number which is a representation of your telemetry. So the reverse procedure is extracting from this big number the three fields, but using the quantization of your destination fields. In this process, you would start with your big number and use the mod function, which is what percentage means, of course, of the number of values of that first variable. You note that they're done in reverse order, and that will give you V3. Now you remove the V3 component from big number by doing an integer divide of that quantization. And then you are left with the higher order digits, and you get the next one by again doing a mod of the V2 size to get V2, etc. Very simple procedure that results in this clever technique. So just, you need to, of course, know what the whisper field quantization is. So I'm just going to briefly go through that. So whisper has three fields, as you know: call sign, grid, and power level. And we need to determine that in order to do the reverse unpacking. Now, call sign is in the form of AA, N, and XXX, where A is alphanumeric and E and N is a number, and X can be A to Z. As you will see later, the call sign, we don't use all of the 6 characters for this reverse encoding, because C1 and C3, the first and third position of the call sign, we are using it to store channel information, and this is required to marry up the whisper original packet with the telemetry packet, because I mean, you can imagine if you receive all these thousands of whisper data packets, how do you know what belongs with what? So we'll see the introduction of a channel just now. So C1 and C3 are fixed, so you can't use that in your quantization. C2 being the alphanumeric, of course, can take 36 values, and C4 to C6 is A to Z, hence 26 each. So if you multiply that out, you'll see you've got 632 and 736 potential values that can be stored in the call sign. The grid has the format of AANN, where A is A to R, which is 18 values, and N is 0 to 9, which is 10 values. So this can accommodate 18 squared by 10 squared, which will accommodate 32,400 values. Then you have, lastly, the power level, which is 19 allowed values, 0, 3, 7, 10, etc., which corresponds to the dB of the power that you're transmitting, which is 19 values. Now, of course, we can't simply decode the call sign using a radix of 632,736, as we saw from the previous slide, because you can't just send a number. The call sign has to be valid in the form of C1 to C6, with the restriction, as you all know, what a call sign looks like. So, in fact, although I said the call sign can accommodate 632,000, etc., you actually have to do it character by character and not simply 3 numbers that you will get by doing the reverse radix unpacking. So a summary of the process is you encode the telemetry values, which is the locator, 56, altitude, temperature, etc., using the mixed radix packing into a big number. And to send this as a whisper packet, we unpack this big number into 3 whisper fields: the call sign, the grid, the power level, using the quantization of these whisper fields. We have effectively transferred our telemetry values, which are 7 of them, into 3 other fields without loss. Now, on the receiving end, to recover the original telemetry, we have to encode the 3 whisper fields, again using mixed radius encoding, into a big number, and then decode by using the quantization of your original telemetry fields back to the original telemetry items. All sounds very confusing. I've got a nice little diagram here to show really what's happening. So on the transmitter side, you have your telemetry, these 7 values, and you use mixed radix encoding to produce this big number. Use mixed radix decoding, and of course remember it was individual call sign characters, not just one number, and you produce these 3 whisper fields, which are familiar, and you can transmit them as a whisper packet. People will receive them, even though the call sign isn't a valid one in the sense of a valid amateur, radio amateur who owns the call sign, but it will be valid in what's allowed in call signs. And again, the grid is not actually the grid of where it is, it's an encoding of this telemetry data. So this gets transmitted and recorded into the WhisperNet database. Then on the receiving side, you will, which we'll see just now through linking, you'll realize that this particular set of call sign, grid, and power are in fact an encoding of some telemetry. So you start by first getting them into a big number, doing the mixed radix encode, which you've seen before. So this is on the receiving side, this part here. So you have the big number, and then you do the mixed radix decoding using the quantization of the 7 known fields. And you would have recovered the 7 telemetry fields that you sent. So just a sanity check to see that, in fact, we can do what we are planning to do as far as quantization and number of values are concerned. So earlier I showed, given that the call sign, grid, and power level can accommodate 632, 736, and 32,419 values respectively, you multiply those out and you see you get this large number, which is 389,512,281, 600 possible values, which is 38.5 bits when encoded into binary. On the U4B telemetry side, I've listed the 7 fields we're encoding and their quantizations or number of values. And if you multiply that all out, you'll find you get the 372 big values. I won't read out the rest of the digits. And that 372 is less than 389. So it is possible to encode these 7 telemetry fields into the 3 whisper fields. So what does this actually look like when it's transmitted? So here's an example of a standard whisper entry, ZR6WT, followed by 2 telemetry packets, because yes, you can send more than one after your whisper entry, which we'll get to later. So there, the first one came in at 1440, the standard whisper recognizable message, which is the call sign and the grid square where it came in and the power that it was sent out. Then is the telemetry packet, which you can see is looks like a nonsense kind of call sign, and also the grid square bears no resemblance to where it was originally sent. It's just an encoding of data, and I'll explain these special characters in a moment. So as I said, if you're transmitting all these whisper packets and telemetry, you need to link them up on the receiver side, because many people could be sending whisper packets and telemetry, and you're going to know whose belongs to what. So the idea was to introduce this channel concept. And for each frequency band, there are 600 channels. And there are 3 aspects that this defines of the whisper telemetry packet. The first is that call sign, the first and third characters. it would set those to a fixed value to indicate which channel it's in. The second aspect is the transmit slot within your 10-minute cycle. Remember, these are all sent within 10 minutes, every 10 minutes. And then finally, the third distinction is the lane or the frequency within the 200 hertz whisper bandwidth to transmit in. So here is the table, which is provided by Triqueta, and the red entries are ones that are already allocated, and the white is available for anyone's use. So the example highlighted is channel 463, which you see in the top of the column is Q3, which means call sign 1 and 3 will use the characters Q and 3 always. It also indicates that the minute here, this is the minute of the TX. So within your 10-minute cycle or window, you will transmit in the 0th minute. And if you had used 464, you would start in the 2nd minute of that 10 minutes. And then the final distinction is the actual frequency or the lane that you must transmit in. So as you know, you have 200 hertz available in the whisper bandwidth. So it's sort of separated roughly into those 4 lanes. And they're the exact frequencies in the example of the 10-meter band. Okay, I realize I'm running short of time. So there are a number of websites that can understand this whisper stuff with the telemetry given the channel. And here's 3 of them, the well-known ones are Triqueta, Whisper, and QRP Labs. The current favorite for me is whispertv.com. It's got lots of extra features. So here is a decoding. If you've given it the channel, it will marry up the various telemetry packets. So here's the original whisper that came in. Here is a telemetry, and you see it was received by 3 different people. And it's identified that it's actually the same thing, because you can see it's the same grid and so on. Only the frequency changes slightly. And this is because of the drift of the VFO of the station receiving it. Because we know it's the same signal that was transmitted. It's got to be the same frequency. So don't worry about that. And then graphically, they also show where the balloon is. So top left shows the overall currents and statistics of the flight. And by clicking on a particular point in the track, the RX stations are shown as yellow dots that receive that particular one. And also you get the specific telemetry detail at that point. So it's showing you there the altitude, the speed, the temperature at that point, the voltage. The sun elevation is not transmitted, but it's calculated by the receiver because it knows exactly where you are, etc. And there it also shows there were 8 people who received it. Here's a nice graphic to show all the Pico balloons currently active in the world. Okay, so I want to also just quickly, but I won't go into the detail, to emphasize that although we have the standard telemetry, which these whisper decoding sites understand and can decode, you're not restricted to that. You can actually define your complete own telemetry, which is called extended telemetry. And the way you would do that, as we saw in the earlier one, you would first send your normal whisper packet. Then you would send a U4B, the standard one, which has got the usual things, altitude and that you would want to send. And then you can send your extended telemetry. However, you're not forced to do that. If you don't want to send a U4B packet and you have your own stuff, you can immediately send your extended telemetry after the whisper packet. They have a more elaborate header, but it still contains this basic type, which you would set to 0, which means extended and not U4B. I won't go into the rest. I've said already that you send your usual whisper packet, the standard U4B, which is optional, you don't have to, and then you have another 3 slots available for non-standard telemetry. So now how do you decode this? Well, there are 2 ways of doing it currently. Triqueter allows you to supply a JSON file to define what your telemetry looks like. So you give it a name, units, and you give the start and end values and the step size. And of course, the step size corresponds to your quantization. So it will take this to know how to encode it into these Whisper fields. So it's generalized. And then on the receive side, you would supply that JSON file to define your values. And here you can see an example of where Triqueter has taken these odd-looking telemetry packets and decoded it. And in this particular example, we were sending the ambient temperature, the humidity, the pressure, and the altitude, where the altitude was calculated from the pressure and not using GPS. And now Whisper TV does the same thing, but you don't use a JSON file to define it. It's all done on the URL, which actually makes it much more versatile. So there's an example. I mean, it looks complicated, but he has a wizard that can generate this URL for you, given what you want to encode. And here's what it looks like on the whispertv.com site. Andy, who wrote the Whisper TV, also came up with a refined custom telemetry as opposed to extended, where you have a much smaller header, which allows you to encode more data. But again, I won't go into that. We're running out of time. And Whisper TV.com goes even further. Besides being able to specify your own telemetry, you can do very clever things, like depending on you might want to alternate. So in one tenant slot, you send one set of telemetry, and in the second one, you send another, because you've got so many things you want to send. So you can put in filters and say, if a particular field has got this value in, decode it this way. If it's got that value in, decode it that way. And all of this is without changing anything to do with Whisper TV or the Whisper protocol, of course. You just encode it in the URL to say how to decode it. Of course, your transmitter must do the special encoding, but that's for you to write. And the rest to receive it, they just receive it and upload it to the WhisperNet. Okay, I'd like to say that's me then. I had to cut that short. Hope it was enjoyable and made sense. Thanks.